Okay, so our next section here is section 6.2, and this is on trigonometric functions. So if you tell your friends you're taking Math 127, usually they'll say like, oh, what class is that? And your answer is trigonometry. So our class is technically classified as pre-calculus 2, but the meat of this whole class is trigonometry. Okay, so trigonometry is the majority of what we're studying here, trigonometry. Okay, and then functions, of course, you learned about functions in your Math 126 class. Okay, so trigonometry. What the heck are we talking about when we say trigonometry? So first up here, I like words. I like Greek roots. Tri means how many? 3. How about this one? Meter. Meter means what? Anybody know? It's a measure. Oh, nailed it. Okay, so we were measuring things with 3 sides. What has 3 sides? Triangles. So most of trigonometry is based on triangles. So we're going to see various types of problems through this chapter, and almost all of them boil down to, let's draw a triangle. Okay, so what we're doing in chapter 6 is what's called right angle trigonometry. And then in chapter 7, we'll extend this to non-right angle trigonometry. Okay, so chapter 6, we're only going to consider right angle trigonometry, which means we're going to be studying a triangle that has 1 right angle. So in a triangle that has 1 right angle, whenever we're looking at freestanding geometric objects, we indicate a right angle with a square corner. This does not apply when we put an angle in standard position on those XY axes. We always indicate an angle in standard position on the XY axes with an arc, even if it's 90 degrees. In freestanding geometric objects here, we'd put a 90-degree angle. All right. Now we have very special names for the 3 sides of a right triangle. The side of the triangle that's across from the 90-degree angle is always called the hypotenuse. Okay, so the side that's across from the 90-degree angle is always called the hypotenuse. The other 2 sides are called the legs. And the legs have special names, but in order to name the legs, we always have to pick an angle of reference. Okay, so most of the time, the angle of reference will be implied by the problem. Usually it's the central angle that hits the origin when our angle is in standard position. Sometimes you have to pick the angle of reference yourself. So what we want to do, we have 2 other angles here. We want to pick our angle of reference. So I'll pick this bottom angle theta. This is my angle of reference. Okay, based on this angle of reference, the leg that is across from our angle of reference theta is called opposite. And the leg that is next to our angle theta is called adjacent. Now let's take the same triangle and pick the other angle as our angle of reference and see what happens. Okay, so here's the same triangle. The side that's across from the 90-degree angle is always called the hypotenuse. Now, the angle of reference we either pick or is given by the problem. We picked this bottom angle, but let's just pick this top angle. I'll call it alpha. The leg that is across from alpha is called the opposite, and the leg that is next to alpha is called the adjacent. Okay, so depending on which angle is our angle of reference, these 2 legs, the opposite and adjacent, they might be labeled differently. So as we go through problems later on in this section, the very first thing we'll always do with a highlighter, circle our angle of reference. So there's no question about which angle is our angle of reference. Then we'll label our sides opposite, adjacent, and hypotenuse based on where that angle is. Okay, so it turns out that triangles have this really interesting property about them. If we look at a teeny tiny triangle, or a medium triangle, or a large triangle, if these angle measurements are the same, we can blow this triangle up as big or as small as we want. And what happens is the ratio of sides stays constant. Okay, so the ratio of sides stays constant. No matter how big or small we make the triangle, if these angles stay the same, right, all we're doing is blowing the triangle up, the ratio of sides stay constant. So for example here, I'm going to do an approximation, but if this angle is 37 degrees, this is an approximation for this example. This is a 3, 4, 5 triangle. If we make it twice as big, these sides are going to be 6, 8, and 10. If we make it 3 times as big, our sides would be 9, 12, and 15. Now, what happens is, as big or as small as this triangle is, if we look at the ratio of sides, ratio means fraction, right? If I look at, for example, the ratio of this side over this side, I would get 3/5. If I look at those same 2 sides here, I would get 6/10, which reduces to 3/5. If we make this 3 times as big, I'd have 9/15, which also reduces to 3/5. That ratio of these 2 sides is always going to be the same number, no matter how big or small we make this triangle. We can look at any of these ratios. So we could do 3/4, 6/8 also reduces to 3/4. Okay, so as big or as small as we make this triangle, the ratio of sides stays constant when this angle is the same. All we're doing is blowing up or shrinking this triangle. Okay, so all of trigonometry is based on ratios of sides of a triangle. We have 3 basic ratios that we care about the most. They are called sine, cosine, and tangent. Okay, sine we abbreviate S-I-N, and we always take sine of an angle. So this is sine of theta. So that means that theta is our angle of reference. Okay, so this tells us our angle of reference. So sine of theta is defined as the ratio of the opposite over the hypotenuse. Our next one, cosine, we abbreviate COS, and we have cosine of theta. So again, that theta, that's the angle we're concerned with. This is going to be the ratio of the adjacent over the hypotenuse. Our next one is tangent. We abbreviate that TAN, and that's the ratio of the opposite over the adjacent side. Okay, so these are our 3 basic trig functions. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent's opposite over adjacent. So that's a lot to remember. So here is something that is really, really handy. If you can remember SOHCAHTOA, this tells us sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, SOHCAHTOA. And I've taught this class like 12 times now, and every time I sit down to do any trig problem, I still think like, oh, I need to find cosine. I still think in my head, SOHCAHTOA. Okay, cosine's adjacent over hypotenuse. Okay, so it's okay to use this on every single problem if you absolutely want. In normal semesters where I do paper tests, I see this written like on every page of my students' tests. They write it over and over and over again. It's very helpful. So SOHCAHTOA. If you need more help remembering this, Google how to remember trig functions. There's all sorts of like funny songs. You might have learned like some old horse can something something, I don't know. But there's stuff online to help you remember this if you can't remember SOHCAHTOA. Any questions so far? Okay, so these are our 3 basic trig functions. The next 3 are called the reciprocal functions, and we don't use these as commonly because all they are is the reciprocals of these 3. So all we're doing, remember, reciprocal means we flip the fraction. So the next three are cosecant, secant, and cotangent. And if you look at a calculator, typically calculators don't even have buttons for these, so they're not as commonly used at all. Cosecant, we abbreviate CSC. This is defined as hypotenuse over the opposite, which is the reciprocal of sine. Secant, we abbreviate SEC. This is defined as the hypotenuse over the adjacent. This is the reciprocal of cosine. Cotangent, we abbreviate COT. That's defined as adjacent over the opposite, which is the reciprocal of tangent. If you are marking your notes, what's really important, you can put this whole thing in a big highlighted box. This is really, really, really important. Okay, so how can you remember what's the reciprocal of what? You can see the way that I've lined these up on purpose. And some mean mathematician, whenever they were naming these things, right, decided to switch the letters. So this is normally how I remember it. So here I have an S and a C, and here I have a C and an S. So it would have been nice if the S went with the S and the C went with the C, but instead they switched them. So usually what I think is the S goes with the C goes with the S, those ones are backwards, and then tangent and cotangent, those words are so similar to each other, it makes sense that those are reciprocals of each other. Okay, so sine and cosecant, those are reciprocals of each other. Cosine and secant, those are reciprocals of each other. And tangent and cotangent are reciprocals of each other. Any questions on this? Anybody need more time on this page? Okay, so let's list out some values of sine, cosine, tangent for some angles now. List of values for the 6 trig functions for both theta and alpha. Okay, so here we have a triangle, a right triangle. We have angles theta and alpha. Okay, so they've asked us to list out the values for the 6 trig functions for both theta, and then we'll do it for alpha. So first we'll start with theta. So we're going to list the values of the 6 trig functions for theta. So that means we want to find sine of theta, we want to find cosine of theta, and we want to find tangent of theta. We'll also find the reciprocals. So sine, the reciprocal of sine is cosecant. The reciprocal of cosine is secant. And the reciprocal of tangent is cotangent. So usually when I'm doing problems like this, I like to line them up in this order on purpose, sine, cosine, and tangent, and then I line up the reciprocal. So the reciprocal of sine is cosecant, the reciprocal of cosine secant, the reciprocal of tangent is cotangent. All right, so first thing we want to think is SOHCAHTOA. SOHCAHTOA, that tells us how to find all of these values. So we have sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Okay, so now what we're going to do is, in order to fill in these values, we need to figure out what sides are opposite, what sides are hypotenuse, what sides are adjacent. So because we are doing all of these problems for theta, we're finding sine of theta, cosine of theta, tangent of theta. That means that theta is our angle of reference. That's what we're computing sine, cosine, and tangent of. So I'm going to circle my angle of reference. The next thing I want to do is based on this angle of reference, I want to label my sides opposite, adjacent, and hypotenuse. So here's where you guys help me out. Theta, this is my angle of reference. Based on where that angle is, let's label our sides opposite, adjacent, and hypotenuse. So I'm going to point at a side, and you guys tell me opposite, adjacent, or hypotenuse. So this is my angle of reference. First up, what is the leg across from that called? What's the leg next to it called? And how about the side that's across from the 90 degree? Hypotenuse, perfect. Okay, so now it's just a matter of filling in these values. So opposite is 3, hypotenuse is 5. So that means sine of theta is 3/5. Cosine is adjacent over hypotenuse. Adjacent is 4, hypotenuse is 5. So that means cosine is 4/5. Tangent is opposite over adjacent, so that is 3 over 4, so tangent is 3/4. Normally we leave these as a fraction. You do not need to convert these to a decimal. On your homework, they'll tell you to leave everything in terms of a fraction. You don't need to, you should reduce them. If they're greater than 1, you don't need to write it as a mixed fraction. Just make sure your fractions are reduced. Any questions so far? Okay. Cosecant is the reciprocal of sine. So that means cosecant is going to be 5/3. Secant's the reciprocal of cosine. So we just take this fraction, flip it over. That means that secant is 5/4. Cotangent's the reciprocal of tangent. That means that cotangent is 4/3. So you should always reduce your fraction, but what you should not do, or what's not necessary, is we like to leave these as one fraction. You don't need to write this as 1 2/3 as a mixed number. Okay, so leave your answer as a fraction, make sure you reduce it if possible, but you don't need to write it as a mixed number. So that's pretty easy. Any questions on that one? Okay, so the second part is let's find the 6 trig functions for alpha. So let's draw our triangle over again from scratch to make sure that we don't make any mistakes here. So now what we're asked to do is find sine of alpha, cosine alpha, tangent of alpha, cosecant of alpha, secant of alpha, and cotangent of alpha. Okay, so we think SOHCAHTOA. So that tells us sine is opposite over hypotenuse. Cosine's adjacent over hypotenuse. SOHCAHTOA, opposite over adjacent. Cosecant's the reciprocal of sine. Secant's the reciprocal of cosine. And cotangent's the reciprocal of tangent. Okay, now all we need to do is label our sides opposite, adjacent, and hypotenuse, and we'll fill them in. Now notice we're doing this for alpha. So now alpha up here is our angle of reference. So again, what I'm going to do is point out the 3 sides, and you guys tell me, based on alpha being my angle of reference, if the sides are opposite, adjacent, or hypotenuse. Go ahead and shout it out. So first up, this is my angle of reference. What's the side next to that called? Adjacent. What's the side across from that called? Opposite, great. And across from the 90 is always hypotenuse. Okay, now it's just a matter of filling in these values in. So we get 4 over 5, 3 over 5, 4 over 3, and then our reciprocals over here. Now you'll notice some patterns between our answers for theta and for alpha, right? These 2 angles add up to 90 degrees in a triangle. So it turns out that we have special relationships between these 2 angles in a triangle and how sine and cosine relate to each other. So you're going to start seeing some patterns as you're working through these problems. And that's common. We see tons of patterns in trigonometry because they all come, trigonometry is all based on these triangles. Okay, so we are picking back up with section 6.2, which is Introduction to Trig Functions. Okay, and remember from last lecture, we had, when we had a right triangle, so we're focusing on right triangle trigonometry. In chapters 7 and 8, we'll do some non-right triangle trigonometry. We had an angle of reference. The side across from the angle of reference is called the opposite. The side next to it is called the adjacent. And the side across from the 90 degrees is always called the hypotenuse. We had 3 basic trig functions: sine of theta, cosine of theta, tangent of theta. Sine is defined as opposite over hypotenuse. Cosine is defined as adjacent over hypotenuse. And tangent is defined as opposite over adjacent. Okay, so our mnemonic for remembering this is so, ka, toa. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent's opposite over adjacent. Okay, so there's a little brief review of what we did last class. We also had some reciprocal functions, which was sine, cosine, and tangent flipped over the reciprocal. Okay, so what we're working on doing now is finding sine, cosine, and tangent of some angle. So for example, you might be asked to find sine of 45 degrees. You might be asked to find tangent of 3 pi over 4. Okay, so that's what we're working up to. Now, as I mentioned, you won't be allowed a calculator on the next exam. So what we're focusing on in this chapter is calculating sine, cosine, and tangent of angles that we can easily do by hand. Obviously, a calculator, you can put sine of any number at all in there, and the calculator will do that. So we're just focusing on ones you can do by hand. So angles, we can easily do by hand. Are going to be multiples of 45 degrees, 30 degrees, 60 degrees, and our quadrantal angles. And maybe you're thinking, Adrian, you wrote that in a really weird order. That's okay. I'll show you why in just a second. Okay, so angles we can easily do by hand. So multiples of, and by do by hand, I mean find sine, cosine, and tangent. We'll be able to find sine, cosine, and tangent of multiples of 45, multiples of 30, multiples of 60, and quadrantal angles. Okay, so remember 45 degrees. Let's, just for funsies here, let's put these in terms of radians. So 45 degrees in terms of radians is pi over what? 4, good. Okay, let's try this one with a couple more people in it. 30 degrees. So what you want to do is think about the ratio of 30 over 180. So 30 degrees is equal to pi over what? Shout it out. 6, good. How about 60 degrees? Pi over what? 3. Okay, so the most common angles we're going to see during this class are multiples of these fractions. So we might be asked to find sine of 3 pi over 4 or cosine of 5 pi over 6, multiples of these. The other angles we can easily do by hand are quadrantal angles. Remember, the quadrantal angles are the ones whose terminal ray sit on the x or the y axis. In other words, these are multiples of 90. Which is, of course, pi over what? 2, good, okay? So these ones are the most common angles we're going to see for the next, for the rest of our class, for the next 3 or 4 chapters. Now, I always tell my students like, oh, this is such a spoiler alert. Because you're not allowed a calculator, any of your homework problems, you're gonna be like, Oh, surprise, there's another 45-degree angle. Oh, big surprise, there's another 30-degree angle, okay? This is gonna get really boring. These are the only ones we can do by hand, so you're gonna see these over and over and over again. But also what this means is if you make a mistake somewhere and you end up with say a pi over 7, you're like, ooh, that's not one of my 4 angles we can easily do by hand. I did something wrong, okay? So it's a good thing and a bad thing. So what we're gonna do is we're going to derive together how to find sine, cosine, and tangent of 45 degrees, how to find sine, cosine, and tangent of 30, 60, and then we'll work on these quadrantal angles. So again, what I'm gonna do, I think it's really important at this level of math that you guys see where these things come from instead of me just like, here's the formula, memorize it. I want you to see where this comes from. And then once we get to our conclusion, I'll put it in a highlighted box for you. Okay, so the reason why I wrote this in this funky order and not 30, 45, 60 is because we're gonna work on the 45 first. Okay, so 45 degrees is pi over 4. Okay, so what I'm gonna do is draw a right triangle that has a 45-degree angle in it. All right, so now let's go back to a little bit of high school geometry. The 3 angles in a triangle always add up to how many degrees? 180. Okay, we are focusing on right triangle trigonometry. So if this angle is 90, that means that these 2 angles always have to add up to what? 90. Okay, so if this is a 45, that means that this is also a 45. We call this a 45, 45, 90 triangle. Okay, so you'll hear me throughout this course like, oh, we got another 45, 45, 90 triangle. Okay, so what our goal is to figure out the ratio of sides in a 45, 45, 90 triangle. And this one's pretty simple. The first thing we'll do is pick an arbitrary length of a side. And what we want to do is pick the easiest side possible, of course. So we're going to pick a length of this side. What is the easiest number to work with? 1. Okay, so let's let this side be equal to 1. Again, going back to some high school geometry, it is true in a triangle if this angle is 45 and this angle is also 45, if these 2 angles are the same, then their opposite sides have to be the same. So that makes this side also a 1. So now we're actually almost done. All we need to do is figure out the 3rd side here. Okay, so remember we have something called the Pythagorean Theorem that we can use anytime we're working with a right triangle. The Pythagorean Theorem says a squared plus b squared is equal to c squared. A and b are the legs, and c is the hypotenuse. Okay, so I have 1 squared plus 1 squared is equal to side c squared. So 1 squared is 1, 1 squared is 1. So I have 2 is equal to c squared. The next step is to take the square root of both sides to solve for c. Now, normally when you take the square root of both sides of the equation, we would put a plus or minus in front of the square root. But because we're dealing with a length here, we only take the positive or the principal square root. So we don't need the plus or minus in front. Okay, so the square root and the square cancel. We get that c is equal to square root of 2. All right, this is the important part. I'm putting in a highlighted box. That means this is really important. The ratio of sides in a 45, 45, 90 triangle, our sides are 1, 1, and square root 2. Okay, so in a 45, 45, 90 triangle, our sides are 1, 1, and square root 2. Now, remember, as I explained in the last lecture, if we take this 45, 45, 90 triangle and we make it smaller, or we make it gigantic, the ratio of sides, sine, cosine, and tangent is going to be preserved. So if I make this twice as big, our sides are 2, 2, and 2 root 2. If I make this 3 times as big, our sides are 3, 3, and 3 root 2. So making this bigger or smaller, the ratio of sides is always going to be preserved, which means we can work with the easiest sides possible, this 1, 1, and the square root 2. Uh-oh, my video froze. Still frozen. All right, those of you guys at home, give me just a second here. Oh, there we go. Okay, we're back. Sorry about that. Okay, so what you need to know is that the sides in a 45, 45, 90 triangle are 1, 1, and square root 2. Any questions so far? Okay, the next one we'll do is the 30 and the 60. Okay, so next up we're going to look at the 30, which is pi over 6, and the 60, which is pi over 3. If we take a look at this triangle, and we want to figure out what the sides are in a triangle that has a 60, you guys just told me that these two sides have to add up to 90, which means that these two angles have to add up to 90, so that means that this angle is 30. Okay, so if we can solve this triangle for those sides, we'll know multiples of 30 and 60 all in one. This is called a 30, 60, 90 triangle. So you'll hear me say this throughout the semester, like, oh, we got another 30, 60, 90 triangle. Big surprise. These are the only two triangles we'll work with in this chapter. Okay. So the derivation of this one takes a little bit more work. So again, I'll show you guys how we come up with the ratio of sides. And then once I get those sides, I'll put it in a highlighted box for you. Okay, so the first thing we want to do is pick the easiest possible side to work with. And you guys just told me the easiest number to work with is the number 1. So the side across from the 30, that's going to be our smallest side. Because this is the smallest angle, I'm going to set that equal to 1. Now, the question is, what is this side and this side? Now, be very careful. Even though this is 30 and this is 60, this is twice 30. That does not mean that this side is twice the length of this side. Okay, so that is not true in triangles. So now we actually have two unknown sides. If you tried to put this into Pythagorean Theorem, you'd have two unknowns, which you can't solve. So this one takes a little bit of a trick. So what I'm going to do is take this 30, 60, 90 triangle, and I'm going to butt it up next to another 30, 60, 90 triangle. We already decided this side was 1. Okay, so now what do I have? If we look at this big outer triangle, this is an equilateral triangle, right? This angle is 60, this angle is 60, this angle is 60, which means that if all the angles are 60, that all three sides are also the same. So this side across from the 30 is 1, this side across from the 30 is 1, which means the total length of the side is 2, which means this side is 2, which means this side is 2. Going back to our picture here, that means the hypotenuse has length 2. Now we can use the Pythagorean theorem to find this third side, right? So Pythagorean theorem says a squared plus b squared is equal to c squared. A and b have to be the legs and c has to be the hypotenuse. So we have 1 squared plus b squared is equal to the hypotenuse, which is 2 squared. So 1 plus b squared is equal to 4. Subtract the 1 from both sides, I get b squared is equal to 3. Take the square root of both sides, I get b is equal to the square root of 3. So here is our conclusion. Again, I'm putting this in a highlighted box because this is important. You need to know this. Okay, so in a 30, 60, 90 triangle, the side that's across from the 30 is the 1. The side that's across from the 60 is square root 3. And the side that's across from the 90 is 2. You need to memorize this. The easiest way to kind of remember what side goes where is it is true in a triangle that the smallest angle is opposite the smallest side, the middle angle is opposite the middle side, and the largest angle is opposite the largest side. So square root of 3 is about 1.7 something. So usually what I do is draw the 30. Across from that gets the smallest side, which is the 1. Then we have the 60. Across from that gets the 1.7, which is the square root 3. And then across from the 90 is the 2. Okay. So we can flip this around, right? If we have this triangle oriented differently, and it looked something like this, a 30, 60, 90, the side across from the 30 is the 1, the side across from the 60 is the root 3, and the side across from the 90 is the 2. And these triangles can be oriented anyway, right? If we have this flipped upside down, the same thing is going to apply. If we have the 30 here and the 60 here, the side across from the 30 is the 1, the side across from the 60 is the root 3, and the hypotenuse is the 2. So regardless of how we orient this, what you want to think about is across from the 30 is the 1, across from the 60 is the root 3, and across from the 90 is the 2. Any questions so far? Okay, so now let's use this knowledge that we just acquired to answer some trig questions. So first example, let's find cosine of 45 degrees. So on your homework or on a quiz or a test, you might see the word find, or the other one you might see is the word evaluate. So if you see the word evaluate cosine of 45, evaluate means find the value. All right, so our steps for solving any of these trig problems are always going to be the same. The first thing we want to do is draw this angle in standard position. Okay, so draw the angle in standard position. So 45 degrees, we put our initial ray on the positive x-axis. 45 degrees is halfway between 0 and 90. Okay, so we're always going to start by drawing the angle in standard position. Step two, we are going to drop a perpendicular from the terminal ray always to the x-axis. Okay, so we're going to drop a perpendicular from the terminal ray always to the x-axis, never to the y-axis. So here's what it looks like. Okay, so this is called a perpendicular. It is perpendicular to the x-axis. You never, never, never draw it to the y-axis. Always drop it to the x-axis. Now, what happens when you drop the perpendicular? It's going to form a right triangle. So our next step is to fill in the angles and the sides. So we knew from drawing this picture that this angle is 45 degrees. That makes this angle 45 degrees. This is one of our two triangles we know how to do by hand. So what I'm going to do is point to the sides, and I want you guys to shout out the lengths of the sides. So first up, across from the 45, this one has length what? 1. How about this one? How about the hypotenuse? Square root 2. Awesome. The next thing we want to do is circle our angle of reference. Circle our angle of reference. Our angle of reference is always going to be the angle that hits the origin. Okay, so the angle of reference is always going to be the angle inside the triangle that hits the origin. The next thing we want to do is label our sides opposite, adjacent, and hypotenuse based on the angle of reference. So this is our angle of reference. The side across from it is the opposite. The side next to it is called the adjacent. And then across from the 90 degree is always called the hypotenuse. Okay. Now that we have our triangle labeled, our final step here is to answer the question. So we are asked to find cosine of 45 degrees. So what we want to do is think SOHCAHTOA. So SOHCAHTOA tells us that cosine is adjacent over hypotenuse. So adjacent here is 1, hypotenuse is root 2. Now we're not quite done. Anytime you're doing these trig problems, there's going to be 3 things you want to ask yourself on your final answer. 1, can I reduce my fraction? 2, do I need to rationalize my denominator? And 3, should my final answer be positive or negative? Okay, so once you get these answers, you should always ask yourself, can I reduce my fraction? Do I need to rationalize the denominator? And should my final answer be positive or negative? Okay, so can I reduce this? No, I'm fine. The second one is, do I need to rationalize my denominator? Yes, absolutely. So what we don't want is a square root in the denominator. Now, maybe you're wondering, why do we even care about that? And this actually comes from us before we had calculators in math. Okay, so if you think about this square root 2, this is an irrational number. It's a non-terminating decimal, 1.41 something, it goes on forever. If you think about the way division works, taking a whole number and dividing by a non-terminating decimal is really, really difficult to do. It turns out if we rationalize this and we do it in the opposite way and we have a decimal divided by a whole number, that division is actually easier to do. So that's the reason why we rationalize the denominator. It stems from back before we had calculators, and it just is kind of carried over in math for years and years now. Okay, so remember from your last math class, how we rationalize our denominator. Rationalize the denominator means we want to get the square root out of it. So what we do is multiply the numerator and denominator by root 2 over 2. The reason why we're allowed to do this, root 2 over 2 is 1, so we're not actually changing the number. In the numerator, multiply across the top. 1 times root 2 is root 2. In the bottom, root 2 times root 2 is equal to what? 2. Now be very careful here. I see students all the time try and reduce this fraction. You cannot reduce something that's under a square root with something that's not under a square root. Okay, so this is our final answer. Cosine of 45 is root 2 over 2. So again, if you look at the different divisions here, 1 divided by 1.41 something, 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 that's hard. But here, 1.41 something divided by 2, that's about 0.7 something. And I can do that really quickly in my head. The third thing you should ask yourself is, should my final answer be positive or negative? I'll get to that in a second. Anytime we're in this first quadrant here, our answer is always going to be positive. I'll show you some examples in a minute here where our answer is negative. On your homework, on your quiz, on your test, you should leave your answer in this form, in fraction form. You should not give your answer as a decimal. It is very standard in trig that we would leave it in this fraction form. Any questions on this? All right, we got one. Let's do some more. Anybody need more time on this page? Okay. Okay, next one, find sine of pi over 3. Okay, so our first step is to draw our angle in standard position. Okay, so there's a couple ways of thinking about this. We know that over to 180 is 1 whole pi. So we want to go 1/3 of the way to 1 whole pi, which ends up being about here. I would encourage you guys to start to get comfortable using radians. If you're not comfortable using radians and you want to convert to degrees every time, that's fine too. The way you want to do the conversion is remember that pi is 180 degrees. Pi radians is 180 degrees. So 180 divided by 3, this is the same as 60 degrees. Okay, so step 1, draw our angle in standard position. Step 2, drop a perpendicular always to the x-axis, which is going to form a triangle. So drop a perpendicular from the terminal ray to the x-axis, that forms a triangle. Our next step is to fill in the angles and the sides. So if this is 60, we know these two angles add up to 90, so this is 30. So as I mentioned before, it should be like, oh, big surprise, we got another 30, 60, 90 triangle. Okay, we only have these two triangles in the class, the 45, 45, 90 and the 30, 60, 90, so you better end up with one of those two. All right, the next thing we want to do is fill in the lengths of the sides. So I'll have you guys help me out with this. The side that's across from the 30 has length what? Shout it out. 1. Okay, let's try everyone else together now. Across from the 60 has length what? Square root 3. And what's the hypotenuse? 2. Okay, so that's how I fill it in. Across from the 30 gets the 1, across from the 60 gets the root 3, across from the 90 gets the 2. Next step is to circle our angle of reference. Our angle of reference is always the angle inside this reference triangle that hits the origin. So the angle inside the triangle that hits the origin. So based on this, we have opposite, adjacent, hypotenuse. Okay, so sine of pi over 3, we think SOHCAHTOA, so tells us sine is opposite over hypotenuse. Okay, so our opposite here is square root 3, hypotenuse is 2. Once you get your answer, there's 3 things you should ask yourself. Can I reduce this fraction? The answer is no. Do I need to rationalize my denominator? The answer is no. Should my final answer be positive or negative? I'll show you some examples where they're negative in a minute here. Anytime we have an angle in the first quadrant between 0 and 90 degrees, our answer is always going to be positive. Any questions on this? Okay, let's do some more. Let's find tangent of 3 pi over 4. All right. Our first step is to draw our angle in standard position. So again, you can either convert this to degrees if you like, or think about this in terms of fractions. So we know that 180 is 1 whole pi. I want to go 3/4 of the way to 1 whole pi. So 3/4 of the way to pi looks like this. So this angle over here is 3 pi over 4, which is 135 degrees if you wanted to do the conversion. So if I did the conversion in my head, first I'd look at pi over 4. We know that's 45. 45 times 3 is 135. Okay, so now we're looking at an angle in the second quadrant. So this is going to look a little bit different. So first step, draw the angle in standard position. Second step, drop a perpendicular from the terminal ray to the x-axis. Drop a perpendicular from the terminal ray to the x-axis, forming a triangle. Our next step is to fill in the angles in the sides. All right. So there's a couple ways of thinking about this. We know that this angle is 3/4 of the way to pi. And we know that all the way to the flat, to the negative x-axis, is 1 whole pi. So if this is 3/4, we ask ourselves 3/4 plus what gives us 1 whole pi? And that would be 1/4, which is 45 degrees. The other way of looking at this is in terms of degrees. If this is 135, we would ask ourselves 135 plus what gives us 180, and we need 45. So 135 plus 45 gives us 180. Or you can do subtraction, right? Pi minus 3/4 pi leaves us with 1/4 pi here. 180 minus 135 makes this 45. So a couple of different ways of thinking about this, but you should end up with either 45, 45, 90 or 30, 60, 90 at least for this chapter. Okay, so that makes this angle 45, which means our sides are 1, 1, and square root 2. Our reference angle is always the angle inside the triangle that hits the origin. Now, you'll notice that we're asked to find tangent of 135, but our reference angle, the angle we're using to get our answer, is 45 degrees. Okay, so this is called a reference angle. This is called a reference triangle. So based on where this angle is, the side across from it is called the opposite. The side that's next to it is called the adjacent, and the side across from the 90 is called the hypotenuse. Okay, so fill in our sides and angles, circle your reference angle, label the sides. Okay, next up, let's answer our question. So we were asked to find tangent of 3 pi over 4. Okay, so now we think SOHCAHTOA. Tangent is opposite over adjacent. Okay, so our opposite is 1, adjacent is 1. 1 divided by 1 is 1. Now we're not entirely done yet, so I'll let you guys all get caught up, and then let's go through the 3 things we should check. First thing we should check, can we reduce our fraction? Certainly 1 over 1 is 1, got it. Second thing, do we need to rationalize our denominator? No. Okay, third question is, should our final answer be positive or negative? Okay, when our angle is in the first quadrant, up here, first quadrant, all of our answers will always be positive. When our angle is in quadrant 2, 3, or 4, we have to ask ourselves, should our final answer be positive or negative? Okay, so if you look at this in terms of x and y coordinates, this adjacent side corresponds to this x coordinate. X on this side of the origin, what are the x values over here? Positive or negative? Yes. Negative. So this actually should be a -1. Let's look at our y coordinate. Our y coordinate, this opposite side corresponds to this y coordinate. Y coordinates up here are what? Positive or negative? Positive, so that's right. The hypotenuse of the triangle is the distance from the origin out to this point on the terminal ray. The hypotenuse is always, 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 100% of the time going to be positive. Okay, so only these opposite and adjacent do you need to ask yourself, are they positive or negative? Okay, so that means this adjacent should be negative, which means our final answer should be -1. Now, there's a shortcut for doing this. There's a shortcut for figuring out should your final answer be positive or negative. So throughout the semester, I don't care if you do it this way or if you use the shortcut. I like the shortcut because it requires way less thinking. You don't have to ask yourself, where's my angle, where's my side, positive or negative. We just use a shortcut. So my shortcut that I like, this is shortcut to determine if your final answer is positive or negative. Okay, so as we go around from 0 to 360, we go through ASTC. I like to remember all students take calculus. Shout out to my high school math teacher, Mr. Miller, who taught me this circa, I want to say 1998. And I still to this day, like, oh, Mr. Miller taught me the best way to remember this ever. Okay, so all students take calculus. This tells us what is positive in that quadrant. Okay, so the way you use a shortcut, in the first quadrant, we have an A. All of our trig functions are positive, A for all. Now, corresponding to triangles, x and y are both positive in the first quadrant, so that's why all of them are positive. In the second quadrant, we have an S. That means that sine is the only one that's positive, which means that cosine is negative and tangent is also negative. The reciprocal functions would have the same positive, negative value. Okay, so if we look at our picture here, this should make sense. Sine has opposite over hypotenuse. Those are both positive. Cosine would be adjacent over hypotenuse. One of those is negative. Tangent would be opposite over adjacent. One of those is negative in the second quadrant. Okay, so sine is positive. Cosine and tangent are both negative. In the third quadrant, we have a T. That means that tangent is positive, which means that sine and cosine are both negative. This should make sense. In the third quadrant, both x and y are negative. So that would make sine negative and cosine negative. Tangent would be opposite over adjacent, so negative over negative would give us a positive. In the fourth quadrant, we have a C. That means that cosine is positive, which means that sine and tangent is negative. And I'll talk you through using this shortcut as we go through more examples. If you hate this, you can certainly figure out what are my sides, positive or negative, and you can do it the long way if you want. Doesn't make a difference to me, whatever you like better. Any questions on this? Okay, let's do some more. Let's find cosecant of -pi/6. Okay, our first step is to draw our angle in standard position. Draw our angle in standard position. So the first thing we notice about this angle is that it's negative. So remember, for a negative angle, we put our initial ray on the positive x-axis, and then we want to move in the clockwise direction. So pi over 6, we think pi is 180 degrees. So 180 divided by 6 is 30. So this is what negative pi over 6 looks like. The next step is we drop a perpendicular from the terminal ray to the x-axis. Now I keep saying drop a perpendicular, but here when our terminal ray is below, what we want to do is just draw from the terminal ray to the x-axis. So drop a perpendicular from the terminal ray to the x-axis, forming a triangle. The next thing I want to do is fill in my angles and my sides. So this one's kind of interesting. We know that this angle, when we drew it in, was negative pi over 6. Now what we're doing is focusing on this triangle. So usually in the triangles, we like to put degrees and not radians. And also we would put positive 30. It doesn't actually make too big of a difference, right? This is an intermediary step. It's not our final answer. So if you label this as 30 or as negative 30 or as pi over 6 or as negative pi over 6, it doesn't really make a difference to your final answer. So you'll see me, I like to label my triangles in degrees. Usually we label geometric objects in degrees and not radians. And usually we measure those, we like to label geometric objects with positive angles. Okay, so that makes us a 60. And again, surprise, surprise, good old 30, 60, 90 triangle. Next thing I'll do is fill in the lengths of my sides. Across from the 30 is a 1. Across from the 60 gets a √3. And the hypotenuse gets a 2. The next thing we'll do is circle our angle of reference. Our angle of reference is always the angle inside our triangle that hits the origin. This one's a little bit backwards and upside down, so I'll help you have you guys help me fill in the names of the sides because we haven't seen a triangle here in this 4th quadrant yet. So what I'll do is point to the sides and I'll have you guys all shout out opposite, adjacent, or hypotenuse. Okay, first up, the side that's across from the 30, this should be labeled what? Opposite, adjacent, or hypotenuse? Opposite. Opposite, great. How about this side? Hypotenuse, all right, which means that this is adjacent. Awesome. You guys are gonna nail the quiz later on today. Okay, so next up, let's answer the question. So we have cosecant of negative pi over 6. Okay, so the first thing we should ask ourselves is cosecant is the reciprocal of what? Sine, cosine, or tangent? Sine. Okay, so cosecant is the reciprocal of sine. So the way I like to remember these is that the letters are backwards. The C goes with S, and then secant's the reciprocal of cosine. The C goes with S, so the letters are flipped. Okay, so now we think about SOHCAHTOA. So SOHCAHTOA tells us sine is opposite over hypotenuse, which means that cosecant is hypotenuse over opposite. Next step, let's fill in our sides. Hypotenuse is 2, opposite is 1, which gives us 2. Now we're not done yet. There's 3 things we need to ask ourselves. Step 1, can we reduce our fraction? We already did that. Step 2, do we need to rationalize our denominator? Nope, good to go. Step 3, should my final answer be positive or negative? Okay, so there's a couple different ways of thinking about this. If you want to use the shortcut, all students take calculus. We have a C. That means that cosine is positive, which means that sine is negative and tangent is negative. The reciprocal functions have the same positive or negative values. So here, if sine is negative, cosecant's the reciprocal of sine. That means that cosecant is also negative. The other way of doing this is by tracking what the x and y coordinates are. So here, this side is the x coordinate, that's positive. Here, this is the y coordinate, that's actually negative. The hypotenuse is always going to be positive. So if you want to track those sides, that means this should be negative, giving us a final negative answer. Any questions on this? Let's do some more. Okay, next one, find sine of 225 degrees. Our first step is to draw our angle in standard position. So when we ask ourselves, where should this angle go? What we want to do is think about angles that we know for sure. So we know 180 is our flat line here, and we know 270 is our third quadrantal angle. Okay, so drawing positive 225, we move in the positive direction. It's going to be bigger than 180 and less than 270, so it should be somewhere in this third quadrant. And in order to get an accurate picture, let's figure out 225 minus 180 is 45. So we need to go 180 plus 45 more. So this angle is 225. Our next step is to drop a perpendicular from the terminal ray to the positive x-axis, forming a triangle. The next step is to fill in our angles and sides. All right, guys, help me out with this one. This whole angle here is 225. What is the angle inside this triangle? What's the angle right here? 45, good. Okay, so to figure that out, we ask ourselves how much past 180 have we gone to get to 225? So 180 plus 45 is 225, or you could do 225 minus 180 is 45. Again, we only know two triangles, so you should always end up with a 45, 45, 90 or a 30, 60, 90. We know our sides are 1, 1, and square root 2. Our next step is to circle our angle of reference. Our angle of reference is always the angle inside the triangle that hits the origin. Based on where this angle of reference is, I'm going to label my sides opposite, adjacent, and hypotenuse. Now you might notice too that the adjacent is always going to be the side along the x-axis. The opposite is always going to correspond to the y-coordinate. That's always true. Let's see. We labeled our sides, opposite, adjacent, hypotenuse. Next step, answer our question. So we were asked to find sine of 225 degrees. We think so katoa, so sine is opposite over hypotenuse. So the opposite is 1, hypotenuse is square root 2. Now we have 3 more steps. First one is, do we need, or can we reduce our fraction, which I guess you could do first or second. No reducing necessary right now. Second step, should we rationalize our denominator? Absolutely. So let's multiply by root 2 over root 2. That gives us square root 2 over 2. Third question is, should my final answer be positive or negative? What do you guys think, positive or negative? Negative, good. Okay, so it should be negative. So there's a couple different ways of figuring that out. If you like my shortcut, all students take calculus. We have a t in the third quadrant, which means the tangent is positive, which means that sine and cosine are negative. Or the other way you could figure this out is by tracking these coordinates. This is a negative x, this is a negative y. So here this should actually be a negative 1. Any questions on this? Let's do one more. Find tangent of 5 pi over 6. All right, so the first step is to draw our angle in standard position. So I like to think of this in terms of fractions. We want to go 5/6 of the way to pi. So we know that to 180 is 1 whole pi. So we're going to go 5/6 of the way there. So it's going to look something like this. So if this is 5/6 in this 180 is 1 whole pi. That means that this angle in here has to be 1/6, right? 5/6 plus how many 6 gives us 1 whole pi? 5/6 plus 1/6 gives me 1 whole pi. So this is pi over 6. In other words, 30 degrees. Next step, drop a perpendicular from the terminal ray to the positive x-axis. Next step, fill in our angles and our sides. Here we got a 60. Our sides are 1, square root 3, and 2. Next step, circle our angle of reference. The angle of reference is always the angle inside the triangle that hits the origin. Next step, label our sides opposite, adjacent, and hypotenuse based on that angle. Next step, let's answer our question. So we are asked to find tangent of 5 pi over 6. So we think SOHCAHTOA. That tells us tangent is opposite over adjacent. Okay, so the opposite here is 1. The adjacent is square root 3. So we need to rationalize our denominator, reduce our fraction, figure out should our final answer be positive or negative. So let's do this rationalization first. To get rid of the square root down here, I'm going to multiply by root 3 over root 3. That gives me square root 3 over 3. Do I need to reduce? No. Remember, you can't reduce anything that's under a square root with something that's not under a square root. Last step is to figure out should my final answer be positive or negative. Let me give you guys a second to think about that. Don't shout it out just yet. So positive or negative. So we're in the second quadrant. You can think about where the x's and the y's are, or you can think about the shortcut all students take calculus. What do you guys think? Should my final answer be positive or negative? Negative, good. So if we use all students take calculus, we have an S. That means that sine is positive, which means that cosine and tangent are both negative. Or if you want to track through the sides, this side is negative. Any questions on this? All right. Now I should put a big fat or. In math, there's usually more than one way to approach a problem. This is called the triangle approach to trigonometry. This triangle approach, you draw the angle, drop in a triangle. We know what the sides of the triangle look like. This is my preferred method of solving trig problems. This is not the only way of doing it. Okay, so I want you guys to be aware, if you had taken math in high school, if you'd taken trigonometry in high school, you might have seen something called the unit circle. The unit circle is basically a big page that instead of calculating these out by hand, it has you memorize them, okay? I am not going to teach by making you guys memorize random stuff. I think that's really, really difficult. My goal for you is, if you're in my calculus class in the fall or somebody else's calculus class, my goal is that you can be able to repeat these things. If I ask you to find sine 225, you can draw that and you can remember like, oh, that's a 45. Oh, those sides are 1, 1. And even if you can't remember what the third side is, Pythagorean Theorem it and find it. Okay, so my goal is that you have recall on this a year from now, 2 years from now. I find that when you ask students to memorize things like a whole page of numbers, the recall on that is much more difficult. Meaning, if I gave you this unit circle now and said, hey, memorize this whole page of numbers, a year from now, if I gave you a blank one and asked you like, okay, now fill this all in, you'd probably be like, buh. That being said, if you have used the unit circle and you have it memorized and you are 100% comfortable with that method of solving trigonometry problems, that is fine. You cannot have a printout of the unit circle on exams, but I have students, I'd say I usually have 3 or 4 that the very first thing they do when they get their test is they take a whole sheet of paper and they draw out this page that they have memorized. If you have it memorized and you want to use it, that is fine with me. If you have no idea what I'm talking about, you Google unit circle and you can see what it looks like. And if you far prefer memorization than working things out, totally fine with me. I think memorizing random stuff is more difficult than using logic, Okay, so I want you to be aware of that this exists. And if you like to memorize stuff, cool. By all means, you're welcome to do that. Any questions on that? Anybody use unit circle in high school? Okay, a couple people. I think it just depends on your professor and the textbook if they want you to memorize it or not. But like when I was in college, I remember I had a roommate, her name was Jenny, and she had this big printout of the unit circle. She like blew it up to this huge page and she had it on the wall in her room, and she's like, my teacher's making me memorize this. And I remember being like, why do you need to memorize this? Let me show you how to do it. So two different trains of thought there. So use whatever you like. And that's kind of the good thing and the bad thing about math, right? The good thing is there's more than one way to approach a problem. Maybe you like one way better than the way I like. That's a good thing. Also could be a bad thing because there's a couple different ways of doing it. So any questions on this before we move on? Okay, so this was computing trig values for multiples of 30, 60, 90, and 45, 45, 90. So the next thing we're going to do is evaluating trig values for the quadrantal angles. So those angles that sit on our positive or negative x and y axis. And again, I'm going to show you kind of the long way, and then I'm going to show you a shortcut. I like the shortcut, so that's what I'll use throughout this course, but I want you to understand where the shortcut comes from. This is still 6.2, yes. Okay, so evaluating trig values for quadrantal angles. So quadrantal angles are the ones that sit on the x or the y axis. So what I want to do is talk you through this, and then I will put the shortcut in a highlighted box. Okay, so again, if you want to draw these pictures and follow along with me, cool. If not, if you just want to listen and then just write down my shortcut, that's fine too. Okay, so let's just start with our simplest quadrantal angle is 0 degrees. Okay, if I ask you to find sine of 0 degrees or cosine of 0 degrees or tangent of 0 degrees, the method we were just using no longer works, right? What we would do is start by drawing in the angle, drop a perpendicular to the x-axis, forming a triangle. Well, that certainly does not form a triangle because it's just a flat line. But the idea behind this, the opposite, adjacent, and hypotenuse sides of the triangle is the same. So what we want to do is think about shrinking triangles. So here's a triangle. The side across from our angle of reference is the opposite. The side next to it is adjacent, and then this is the hypotenuse. Okay, so let's think about this. As we get closer and closer to 0, this triangle shrinks and shrinks and shrinks. This side, the opposite, shrinks down as we get closer and closer to 0. This side shrinks down to, what do you guys think? Yeah, 0. When we're at 0, this opposite side is actually 0. Now let's look at what happens to the adjacent and the hypotenuse. As we shrink this triangle closer and closer and closer to 0, the length of these two sides, as we shrink this all the way down, the hypotenuse and the adjacent actually become equal to each other, which means that cosine, adjacent over hypotenuse, would be 1 because these sides are actually equal. So from looking at this, the first thing we know is that sine of 0 degrees, sine is opposite over hypotenuse. As this triangle shrinks down, opposite becomes 0. 0 over any number is 0. Cosine, adjacent over hypotenuse, these approach the same value as we shrink down to 0. Cosine is going to be 1. Now don't worry, I'm going to give you a shortcut for remembering these. This is kind of the long way. I want you to think about this. Okay, next one, let's look at 90 and then we'll list out the shortcut. Okay, so again, if we want to evaluate sine or cosine of 90, and we'll get to tangent in a second here, we think about triangles. So if we were to draw this angle, drop a perpendicular to the x-axis, that does not form a triangle. Okay, so what we want to do is think about triangles that are approaching 90 degrees. So here's a triangle. Here's one that's approaching 90, and we can get closer and closer and closer to 90. So what we want to think about is what happens to the sides of this triangle as we approach 90. So here's our angle theta. This is the adjacent. This is the opposite. This is the hypotenuse. So as we get closer and closer to 90, this adjacent side actually shrinks to 0, which means that cosine of 90 is going to be 0. As we move this closer and closer and closer to 90, these two sides, the opposite and the hypotenuse, approach the same length. So that means that sine of 90 is going to be 1. Again, you do not need to memorize this. I'll show you the shortcut in just a second. But I want you to see where the shortcut comes from. Any questions so far? Okay, so how do you remember all of this? This is my favorite shortcut. And you'll see me draw this over and over and over and over and over again throughout this course. All right, what we're going to do to remember these values is we're going to look at a point that is a distance of 1 away from the origin. Now, the reason why we're using 1 is because this is going to tell us the ratio of sides here. So what we're going to do is list out the x and the y coordinates of each of these 4 points. Okay, so this is a distance of 1 away. The x coordinate here is 1. The y coordinate here is 0. Up here, this is a distance of 1 away. The x coordinate is 0. The y coordinate is 1. Okay. A distance of 1 away, the x coordinate is -1. The y coordinate is 0. Down here, a distance of 1 away, the x coordinate is 0. The y coordinate is -1. Now here comes the shortcut. These go in alphabetical order. Cosine, sine, cosine, sine, cosine, sine, cosine, sine. So let's see how this matches up with what we just figured out. This is 0 degrees. At 0 degrees, cosine of 0 degrees is 1. That's what we figured out up here. Sine of 0 degrees is 0. That's what we figured out up here. Let's look at 90. This is 90 degrees up here. This says cosine of 90 is 0. That's what we figured out right here. This says sine of 90 is 1. That's what we figured out right here. The reason why this works out in terms of x and y coordinates is if we look at a generic triangle, this side is the x coordinate, this side is the y coordinate. The hypotenuse is either the radius of the circle, or here we're doing a distance of 1 away. Cosine would be adjacent over hypotenuse, which is just the x coordinate. Sine would be opposite over hypotenuse, which is just the y coordinate. And then how do we find tangent? Tangent of theta is opposite over adjacent, so that's going to be y over x. Or sine over cosine. Right, sine would be opposite over hypotenuse, cosine is adjacent over hypotenuse. The hypotenuses cancel out, and we just get sine over cosine. So let's list out some values. Sine of 0, looking at this, here's 0 degrees. The s is 0, so sine of 0 is 0. Cosine of 0 degrees, here we have a 1, so that means cosine is 1. How about tangent now? Tangent of 0 is going to be sine over cosine, or y over x. Okay, so sine over cosine is 0 over 1. 0 over 1 is equal to what? 0, good. Okay, let's do 90 now. How about sine of 90? So we look at 90 degrees. Here's 90 degrees. We go up to this point. We have the s is 1, so that tells us sine is 1. Cosine of 90. We go to 90 degrees, we have that c is 0, so that's 0. Here comes the fun part. Tangent of 90 is sine over cosine, so 1 over 0. 1 over 0 is equal to what? Undefined. Okay, so remember, this is one of our key mathematical rules. We have 2, right? We cannot divide by 0, and we can't take the square root of a negative number. Those are the key rules we cannot break. You're not allowed to divide by 0, so this is undefined. Any questions on this? Okay, let's go out to the next quadrantal angle, which is 180. So let's find sine of 180. So we go out to 180. Here's our point. Sine is 0. Cosine of 180, we go out to 180. Cosine is -1. Tangent of 180 would be sine over cosine, or y over x. So 0 over -1 is 0. If we went out to 270, we'd get sine of 270 is -1. Cosine of 270 is 0. Tangent would be -1 over 0, which is undefined. Okay, and this works for any quadrantal angle, positive or negative. All we have to do is go out to that angle, look at this point that's a distance of 1 away, and that tells us how to compute this. And we'll get plenty of practice through this, with this through the next chapter. Any questions on this? Any questions? Anybody need more time? Okay. I have 2 more examples for section 6.2 that are worded just a little bit differently, but they all boil down to the same type of problem. Okay, so next one, let P equal 12, -5 be on the terminal side of theta. Find the values of the 6 trig functions. Okay, so the first thing we always want to do is draw a picture. So we are given a point. They give us the point 12, -5. So here's the point 12, -5. They tell us this point is on the terminal side of theta. So we don't know if theta is positive or negative, but we know that this is the terminal ray for theta, and it actually doesn't matter if we're measuring a positive angle or a negative angle, because we're trying to find the 6 trig function. So our process is the same, regardless of if theta is the positive angle or the negative angle. We have our angle drawn in. The next step would be to drop a perpendicular to the x-axis, forming a triangle. The next step is to fill in our angles and sides, if possible. Now in this problem, we actually don't know what these angles are, but that's okay. In order to find the 6 trig functions, what we need to know is the opposite, adjacent, and hypotenuse. Okay, so let's take a look at this problem. Help me out with this. We can't fill in the angles, but we can certainly fill in the sides. What is the length of this side of the triangle? 12, yeah. What is the length of this side of the triangle? 5, or if you want, you can put in -5. Length, we would say 5, but the y coordinate here is -5. How about the third side of the triangle? Oh, I got somebody 1 step ahead of me, 13. Okay, so whenever you have 2 sides of a right triangle and you want to find the third side, we're going to use Pythagorean theorem. So Pythagorean theorem says a squared plus b squared is equal to c squared. So here I have 12 squared plus 5 squared is equal to c squared. 12 squared is 144, 5 squared is 25. 144 plus 25 is 169. Take the square root of both sides, we get c is equal to 13. So what do I expect you to know by hand? You should know up to perfect squares up to 13. I wouldn't expect you to know higher than that by hand. So you should recognize that 169 is 13 squared. You should recognize that 144 is 12 squared. So you should know up to 13. This is a very common Pythagorean triple. A Pythagorean triple is 3 integers, whole numbers, that satisfy the Pythagorean theorem. So the other good Pythagorean triple that we see a lot is a 3, 4, 5 triangle, and then we'll see this 5, 12, 13 triangle. The only way this works is if the 13 is the hypotenuse. If we had 5, 13 here, this third side would not be 12. Okay, so the largest side has to be that hypotenuse. All right, next step, we circle our angle of reference, which is the angle inside the triangle that hits the origin. Label our sides opposite, adjacent, and hypotenuse. Next step, let's answer our questions. So let's find sine of theta. Sine of theta is opposite over hypotenuse. And in the fourth quadrant, sine is negative. If you wanted to track through this negative, you could do that as well. Next up, cosine of theta, we think so katoa. So cosine is adjacent over hypotenuse. And in the fourth quadrant, cosine is positive. Third one, tangent of theta. So katoa, tangent is opposite over adjacent. And in the fourth quadrant, tangent is negative. If you wanted to track through this -5, that's where that comes from. Our reciprocal functions, cosecant's the reciprocal of sine, so that's -13/5. Secant's the reciprocal of cosine, so that's 13/12. And cotangent's the reciprocal of tangent, so that's -12/5. Any questions on this problem? Any questions? Okay, I got one more example from this section and it looks a little bit different. So I just want you guys to realize as you're going through the homework, if the problems are worded a little bit different, they still boil down to the same thing. Draw the angle, fill in a triangle, find the sides, find the lengths of the sides, answer the question. So this is where, if you had learned in high school, the unit circle, where that kind of falls apart, right? Because the unit circle doesn't account for angles that you don't know. So if you, am I frozen again? Oh no. Okay, those of you guys at home, I think my screen is frozen again. I'm just gonna shut this down and pull it right back up for you guys. Okay, I think we're back on now. Okay, one more example. List the values of the 6 trig functions using the point p equals 1/2, comma, square root 3/2 on the unit circle. Okay, so the first thing we want to do is draw a picture. So they give us a point that is 1/2 square root 3/2. So here's this point, 1/2 square root 3/2. Now they tell us it's on the unit circle, which don't be confused with that page you have to memorize. Unit circle is a circle of radius 1 that's centered on the origin. So what we know about this point, because this point is on the unit circle, is that this distance is 1. Okay, so a unit circle is just a circle of radius 1 that's centered on the origin. Now we can do this exactly the same way as before. we drop a perpendicular to the x-axis. This side has length 1/2. This side has length square root 3 over 2. And because this point is on the unit circle, this side has length 1. If you had not had recognized this term, unit circle, you could have used the Pythagorean theorem with these two values to find that the third side is 1. Now, technically, because we're using a point and not an angle, right? They didn't say find the 6 trig functions of theta. They said find the 6 trig functions using this point. Technically, we wouldn't put theta in our equation. We would put a different variable, and usually we would use t. So it works out exactly the same, but I want you to be aware that on your homework, if you see something like this, you might be asked find sine of t. The reason why they use this other variable is because nowhere in this problem actually has an angle theta. Your textbook has this method where they introduce a t-axis, and so you end up with a t in here. Doesn't matter, just a dummy variable, it works exactly the same way. So sine of t is opposite over hypotenuse. Here's our angle of reference. So here's opposite, adjacent, hypotenuse. Okay, so opposite is square root 3 over 2, hypotenuse is 1. So we just have square root 3 over 2. Cosine is adjacent over hypotenuse. So adjacent here is 1/2, hypotenuse is 1, so we just get 1/2. Tangent is opposite over adjacent. So opposite is square root 3 over 2, adjacent is 1/2. All right, let me let you guys catch up, and we'll talk about simplifying this fraction and the easier way of doing it. Okay, so anytime you have a fraction over a fraction, you can either take the numerator, switch to multiplication, and then flip the denominator, or the way that's much easier is we are always allowed to reduce common factors between the numerator and the denominator. So if we had a multiple of 3 up here and a multiple of 3 down here, we could reduce those. The same thing applies for factors that are fractions, meaning the numerator has a factor of 1/2, the denominator has a factor of 1/2. So we can actually cancel out these 1/2s, just giving us square root of 3. When you're doing trig, since these are usually both the hypotenuse, you're going to see this happen a lot. Now, what have you noticed here? Hopefully, when a point is on the unit circle, meaning the radius is equal to 1, it is true that sine of t is always just the y coordinate. Cosine of t is always just the x coordinate. And tangent is always y over x. Okay, so if we're looking at a point x comma y, this works just like we did with the quadrantal angles. They go in alphabetical order. This is cosine, this is sine. Now, why is this true? If we look at a generic triangle, this side is x, this side is y. On the unit circle, this side is 1. Sine would be opposite over hypotenuse, that's just y. Cosine would be adjacent over hypotenuse, that's just x. Tangent would be opposite over adjacent, that's y over x. So if you would like to use these shortcuts, you're welcome to. You don't have to use these shortcuts. It always works out that you can draw in the triangle and do opposite over hypotenuse, adjacent over hypotenuse. But there are these shortcuts only when the point is on the unit circle. We were asked to find all 6, so let's just quickly list out the last 3. Cosecant is the reciprocal of sine, so that's 2 over root 3. Rationalizing that, I get 2 root 3 over 3. Secant is the reciprocal of cosine, so that's 2 over 1, which is 2. And cotangent's the reciprocal of tangent, so that would be 1 over root 3. Rationalizing that, we get root 3 over 3. Since we're in the first quadrant, all of our trig expressions are positive.